All right, we are going to continue with figuring out how to find determinants of matrices. And I'm going to work here with some of these row operations to simplify A just a little bit. If I end up doing 2 row 1 plus row 2 into row 2, I get 0 and then 0 again and -5. And if I end up adding row 1 and row 3 and putting that into row 3, I get 0, 3, and 2. Well, if you remember from what we did in the last video, if I can get this into a triangular matrix, then I can just multiply down the diagonal to find my determinant, right? But you have to be careful here. Whenever we interchange 2 rows, okay, then I'm going to have to take the negative. So when I interchange these 2 rows, I have to have a negative on the outside when I go in to find my determinant here. But now I can just multiply straight down. 1 times 3 times -5 gives me -15. And so my final answer is 15 here. Now, if you notice on C, where it says you can factor out a common multiple of 1 row, then you can say the determinant of B is K times the determinant of A. We're going to use that in this next example. So let's scroll down to that. All right, so we have a 4 by 4 matrix here, and I want to figure out the determinant. Now notice the first row does have a factor of 2. So let's go ahead and take out a 2 and then divide that top row by 2. Everything else stays the same. I don't see any other common factors of any other rows, especially some of these with zeros in them. All right, doing some row reduction here, I can go ahead and get rid of my first set of columns. And when I do that, I get 0, 3, -4, -2, 0, -12, 10 and 10, 0, 0, -3, and 2. All right, let's continue to doing some row reduction to seeing if I can get this into a triangular matrix versus trying to do a cofactor expansion. Okay, you could do a cofactor expansion here on that first column, but then I don't really have a lot of other zeros. So let's do just one more row reduction, maybe 2 more row reductions, and see if we can get this. So this is going to be 2 times, let's leave the first 2 columns alone. If I do 4 times row 2 and add it in, I end up getting a -6 here and a 2 here. And then if I do a twice row 4 and add that to my new row 3, I end up getting this here. All right, so now I can just use my diagonal here, and I know that my determinant must be 2 times 1 times 3 times -6 times 1, which gives me -36. Now, if we have a square matrix, we have it in this row reduced form, and that determinant, okay, is not 0. And if there are interchanges, okay, in between those row reductions, then you're going to do -1 to the r, the number of times that you had to change rows around, right? That's based off of the b, and then times the determinant of u. It's also true that you can do -1 to the r and then the product of the pivots in u when a is invertible. Because if a is invertible, then all of those are going to end up being pivots, versus when they're not, right? Then I'm going to end up getting u is equal to 0. So if a does not have an inverse, then the determinant is going to end up being 0. Okay, and so this is interesting to note. It says that although the echelon form of u described above is not unique because it's not completely row reduced, the pivots are not unique, and the products of the pivots is unique, except for the possible minus sign. So the product of the pivots, okay, is going to be a number that is unique to that square matrice, no matter what, except for maybe a plus or minus sign. Okay, Formula 1 not only gives us a concrete interpretation of the determinant of A, but also proves the main theorem of this section. And let's go ahead and look at this example, okay? I'm actually going to go ahead and write this theorem in here. I should have done it in our notes. So theorem 4 in this chapter says a square matrix A is invertible if and only if the determinant of A is not equal to 0. Perfect. All right, so let's go ahead and look at this example here. I'm going to go ahead and add in 2 times row 1 into row 3. And when I do that, I now have 0, 5, -3, -6. And then in this third row, I have 0, and that's a positive 5 there, -3, -6, and I'm just going to put in this last row here. So I have a repeat, right? I have a repeat row here. So I don't have the right number of pivots in my rows and pivots in my columns, because these are going to end up canceling out. So I can right away already say that my determinant of A is 0. Okay, because I don't have an inverse of this matrice. And this theorem here says that I only have an inverse, okay, if the determinant is not 0. So this one does not have an inverse. Determinant is going to be 0. Let's go ahead and look at one more example here. So here I have a matrix, and before I start switching things around, because I see that top one isn't 0, let's actually just take R2 plus R4 and put it into R4. So what does that do? 0, 1, 2, -1, 2, 5, -7, 3, 0, 3, 6, 2. I get 0. Oh, sorry, that should be 0. -3 and 1. All right, using a cofactor expansion here through that first column, excuse me, I know that this is then 2 times, omit that second row here. Now, because this is in this space right here, that's actually going to be a -2 out in the front. If you do -1 to the, let's see, this is 2 plus 1, technically, I'm going to end up having a negative out here, right? Okay, can I do some row reduction inside this first? So let's do -3r1 plus r2 into r2. That gives me 0, 0 again, and then 5, 0, -1, and 3. And then I'm just going to go ahead and switchy these, but remember when you switch, you're going to take the negative on the outside, right? Okay, so I have 2 times 1 times -3 times 5, and I end up getting -30 as my determinant.